Imagine Earth from space. Not blue and green, but almost white, a planet wrapped in ice, ocean, and a silence unlike anything today. This is the radical possibility behind Snowball Earth, that ice once reached almost every ocean, while continents endured beneath a dimmer sun. The idea sounds like science fiction, yet its strongest arguments are not imagined landscapes. They are layers of stone preserved across ancient continents. Some of those rocks began as mud, sand, or volcanic ash, deposited when the world was cold enough to move glaciers across seafloors. Their message is startling because many deposits now sit in places that were once near the tropics, where geologists would expect warmth, not ice. The evidence does not come from one famous outcrop. It appears on several continents, separated by oceans and time, yet repeating the same unsettling pattern. In the field, a geologist may see a rough, chaotic layer, packed with stones that glaciers carried, dragged, and abandoned without sorting. Elsewhere, the rock record shows surfaces scraped by moving ice, then buried beneath sediments laid down after the frozen machinery finally stopped. These clues matter because climate leaves no single signature. Instead, it writes through sediment, minerals, chemistry, and the geography of vanished oceans. Together, they raise a question immense enough to challenge our intuition. Could Earth really lock itself inside a global climate trap? The answer begins with a planet that was already changing, as shifting continents altered ocean currents, weathering, coastlines, and the balance of carbon. Then, perhaps, cooling pushed snow and sea ice farther from the poles, brightening the planet and reflecting more sunlight back into space. That reflection created a dangerous feedback. The whiter Earth became, the less solar energy it absorbed, and the easier further freezing became. At some threshold, a cooling trend may have become a runaway transformation, carrying ice from polar margins toward the equator. If that happened, sunlight would weaken beneath clouds and haze, seasons would lose their familiar rhythm, and the ocean surface could harden almost completely. Yet the planet would not become geologically dead. Volcanoes would still burn, tides would still move, and life would still search for openings. That tension is what makes the hypothesis so powerful. A frozen surface could conceal a world still driven by heat, chemistry, and survival. The geological record also hints these episodes were not isolated accidents, but repeated crises separated by intervals when ice retreated and oceans reopened. Some glacial rocks appear in formations of astonishing age, while similar evidence turns up far away, suggesting more than one near global freeze. But rocks do not preserve a movie. They preserve fragments, and every fragment must be tested carefully against competing explanations. A deposit might record a glacier, a peculiar ocean current, or a local climate anomaly. Context determines whether the clue becomes a global story. That is why scientists compare rock types, ages, locations, and chemical signals, searching for patterns too broad to belong to one valley or coastline. The deeper the comparisons go, the stranger the picture becomes. Ancient ice seems to have reached extraordinary distances, then vanished with astonishing speed. To understand how that could happen, we must enter the cryogenian world before tracing its continents, oceans, and climate toward the tipping point. There, beneath the evidence, lies the central mystery. How did a living planet become white, and how did it find its way back? Before the planet turned white, Earth was already entering a strange interval, later called the cryogenian, beginning roughly 720 million years ago. It was not a frozen world at first. Warm seas, active shorelines, and broad continental interiors supported a planet in constant geological motion. The continents, however, were gathering into a configuration that would soon matter enormously. The ancient supercontinent Rodinia was beginning to come apart. Rodinia had assembled long before this era, welding huge land masses together across the globe and leaving deep scars where ancient oceans had disappeared. Now, those scars were reopening. Crust stretched, faults awakened, and molten rock rose through widening fractures as new ocean basins began to form. Rifting did more than redraw coastlines. It changed elevation, exposed fresh rock, and altered the paths by which seawater and atmosphere exchanged heat. As landmasses shifted toward new latitudes, familiar climates moved with them, carrying deserts, rainfall belts, shallow seas, and biological communities into unfamiliar surroundings. That movement unfolded slowly by human standards, yet geological time magnified every consequence. A coastline could migrate, vanish, and return under entirely different conditions. The oceans were changing too. New seafloors opened space for currents, while submerged margins created broad shelves where sediments accumulated in layers. Those layers became a quiet archive, recording the chemistry of seawater, the minerals washing off continents, and the biological activity of ancient coastlines. In some regions, volcanic plateaus rose above the rifts, releasing gases and minerals while newly formed mountains began wearing down under rain and wind. Weathering was especially important because fresh rock can draw carbon dioxide from the atmosphere, linking tectonic upheaval to long-term climate change. Yet no single process worked alone. Ocean circulation, volcanic activity, sunlight, and the position of continents combined into a climate system with many moving parts. The sun itself was slightly dimmer than today, a background difference that made Earth's climate more sensitive to shifts in atmospheric composition. Life was already experimenting with new forms. Microbial mats spread across shallow waters, while early complex cells occupied niches beneath the visible surface. On land, there were no forests or grasslands. Bare mineral surfaces met the atmosphere directly, making geology a powerful influence on climate. Even the shape of the planet's coastlines mattered, because shallow seas could absorb heat, host reactions, and connect distant environments. When geologists reconstruct this vanished geography, they are not simply drawing an old map, they are rebuilding the conditions beneath an ancient climate. They use matching rock belts, magnetic signatures, and the ages of mountain chains to trace continents that now lie thousands of miles apart. A volcanic province on one continent may align with a broken fragment on another, revealing a former connection hidden by later oceans. These reconstructions show Rodinia was not a static slab, but a stressed network of sutures, rifts, uplifts, and margins facing restless seas. As it fragmented, the planet gained more exposed coastline and fresh rock, creating new opportunities for chemical exchange between land, ocean, and air. The consequences were not immediate, and they were not uniform. Some regions warmed beneath humid skies, while others cooled beside rising ice-prone highlands. That unevenness is crucial. Earth did not switch from normal to frozen in a single instant. It approached a threshold through countless regional changes. To understand what happened next, we must follow those changes into the atmosphere, where small imbalances could eventually become planetary consequences. A climate rarely freezes all at once. It cools in stages, until one reinforcing process becomes stronger than every warming influence around it. Imagine Earth already cooler than today, with bright seasonal snow lingering longer, especially across high latitudes where sunlight arrives at a shallow angle. That snow matters because its pale surface reflects incoming sunlight, returning energy to space instead of allowing dark ground or ocean to absorb it. As reflection increases, the surface loses more heat, temperatures fall further, and snow survives through seasons that once would have erased it. This is the first turn of the feedback. Cooling creates snow, snow reflects sunlight, and reflection creates still more cooling. Ice can then advance from mountains and polar margins, covering darker landscapes and narrowing the open water that once stored solar warmth. The crucial threshold arrives when seasonal ice no longer melts completely, leaving a permanent patch ready to grow during the next cold season. Ocean water is darker than ice, so every newly frozen expanse changes the planet's reflectivity and amplifies the original temperature decline. Meanwhile, continents introduce their own complications. Uplifted rock can weather rapidly, drawing carbon dioxide from the air and weakening the greenhouse effect. If fresh mountain belts rise beneath a cooling atmosphere, chemical weathering may accelerate, quietly removing another blanket of warmth from the planetary system. Changes in ocean circulation can reinforce that trend, carrying less heat toward the poles and allowing cold water to spread beneath expanding sea ice. A rearranged continent may also block warm currents, expose new rock, or place larger areas at latitudes where freezing becomes easier. The atmosphere responds slowly, but the surface responds immediately. Each white margin shifts the balance between absorbed sunlight and escaping heat. At first, open water remains a powerful heat source, releasing warmth and moisture into the air whenever winter darkness reaches the surface. But as ice thickens, that exchange weakens. The ocean becomes more insulated, while sunlight reflects away before it can recharge the surface. The boundary between ice and water becomes a moving front, advancing whenever freezing gains even a small advantage over melting. Clouds add uncertainty because they can reflect sunlight like snow, yet also trap infrared radiation, making their net influence depend on altitude and season. Dust and volcanic aerosols may darken ice locally, but their effects are patchy, while the broad reflectivity of a growing ice sheet remains dominant. Once ice reaches lower latitudes, the planet enters a more dangerous regime, because bright surfaces now occupy regions receiving stronger sunlight. There, a modest expansion can reflect enough energy to cause further cooling, turning a local advance into a hemispheric transformation. The process does not require every part of Earth to freeze simultaneously. Connected ice fields can spread the feedback across oceans and continents. As open water disappears, evaporation declines, rainfall patterns shift, and ecosystems lose familiar coastlines, even before the most severe freezing arrives. Eventually, the climate can settle into a state where melting becomes difficult, because incoming sunlight is reflected and greenhouse warming has already weakened. Volcanoes still erupt, tides still move, and life still exchanges gases, but the surface has lost its easiest routes back toward warmth. From this point onward, the frozen world is governed by a new balance, one that the rocks may later reveal in remarkable detail. As the ice spread across the ocean, the surface became a white lid, but beneath it, water remained a hidden, slowly changing world. From above, thick sea ice would have looked nearly motionless, its snow cover muting waves and sealing the dark ocean from the open sky. Yet the frozen shell was not uniform. Currents, salinity, and heat from below could keep some regions thinner, weaker, and more active than others. Where ice stayed translucent, faint sunlight entered the upper layers, creating narrow bands of illumination beneath a ceiling that looked completely closed. In those dim zones, microscopic organisms could gather along the underside, using brief pulses of light to build energy from dissolved carbon. Freezing also changed the water chemically, pushing salt into concentrated brine channels that threaded through the ice like hidden veins. Those heavy brines sank beneath the surface, carrying nutrients downward and stirring a slow circulation inside an ocean otherwise trapped beneath frozen water. The circulation was weak compared with modern seas, yet over long intervals it could redistribute heat, minerals, and the chemical ingredients life required. Far below, volcanic activity never stopped. Magma continued warming the crust, while seafloor vents released hot fluids into the buried ocean. Around those vents, heat and chemicals supplied energy without sunlight, supporting microbial communities adapted to darkness, pressure, and extreme concentrations of dissolved metals. The vent fields were isolated islands of habitability, separated by vast stretches where metabolism slowed, and every usable molecule became precious. Above the ice, volcanoes added another kind of pressure, releasing carbon dioxide and sulfur gases into an atmosphere with nowhere else to go. Because rainfall and weathering were greatly reduced, those gases could accumulate, slowly strengthening the greenhouse effect while the frozen surface reflected most sunlight. Volcanic ash and wind-blown dust sometimes settled on the ice, darkening patches and allowing them to absorb more of the weak seasonal sunlight. A darkened patch could warm, soften, and enlarge, forming a temporary melt pond where light and atmosphere touched water again for a short season. Such openings were probably local and fragile, but they offered moving windows through which gases exchanged and surface communities might briefly flourish. Along coastlines, tides could fracture the ice, exposing narrow leads that refroze repeatedly and concentrated nutrients at the margins of darkness. Geothermal warmth created other refuges, especially where hot springs, shallow rock, or thin ice connected the ocean with the atmosphere. These refuges did not need to resemble modern ecosystems. Survival alone could mean dormant cells, slow feeders, or microbes trading chemicals in darkness. Life may also have endured inside pores and cracks, protected from crushing ice and buffered against sudden changes in salinity, temperature, and acidity. In this hidden biosphere, evolution would have favored efficiency over speed, recycling every trace of carbon and tolerating long periods of scarcity. The frozen ocean, then, was not a blank interval in Earth's history, but a place where change continued at a nearly invisible pace. Its climate, chemistry, and living communities were still responding to one another, even while the planet's surface appeared locked beneath permanent winter. And that distinction matters, because the rocks left behind record not only ice, but the restless processes continuing beneath its frozen cover. When the world finally thawed, those buried signals emerged with the glacier's debris, preparing the evidence we will examine in rocks laid down afterward. The first clues are not frozen landscapes, but rocks, jumbled sediments, stranded stones, and polished surfaces that preserve ice's vanished movement. Across continents, these deposits share a distinctive texture, with clay, sand, pebbles, and boulders mixed together without the sorting water usually provides. Geologists call such poorly sorted material tillite, when ancient burial and cementation transformed glacial till into durable sedimentary rock over time. A river tends to arrange its cargo by size. Moving ice behaves differently, carrying fine mud beside house-sized blocks, then releasing everything together. That chaotic mixture is a fingerprint of transport within or beneath a glacier, where immense pressure drags debris forward through a slow, grinding journey. In the field, a dark bed may look ordinary until a fresh cut reveals angular fragments suspended in a compact, muddy matrix. Some clasts are scratched, faceted, or flattened, shaped as stones grind against one another and the bed beneath moving ice. The largest blocks can be strangers to their surroundings, carried far from their source and left behind when the ice finally retreated. These transported boulders, called erratics, allow scientists to compare the rock they sit on with the distant terrain that supplied them. A single erratic proves movement, but a field of mismatched boulders reveals a vanished conveyor belt, its direction encoded across the landscape. The trail becomes clearer where ice once scraped its bed, cutting parallel grooves into stone and leaving a surface known as a glacial pavement. Those striations are not random weathering. They are linear scars, often pointing along the former flow of a long-vanished ice sheet. When grooves cross an ancient rock surface beneath tillite, the sequence records contact. Bedrock first, moving ice next, sediment afterward. The evidence becomes startling when these scars appear in strata that formed near the equator, according to magnetic minerals and ancient sedimentary structures. Tropical-looking rocks may contain shallow water features, warm climate soils, or carbonate platforms, yet ice later bulldozed across their exposed surfaces with unmistakable force. That juxtaposition creates the puzzle. Not merely cold deposits, but unmistakable glacial action recorded beside, and sometimes directly upon, rocks of low latitude. Paleomagnetism helps locate those ancient beds, because magnetic grains can preserve the orientation of Earth's field as sediments settled and later hardened. By combining that compass with sedimentary clues, researchers reconstruct coastlines, ice flow paths, and the remarkable distances debris traveled before deposition. Yet the record is rarely pristine. Mountains erode, faults repeat layers, and later oceans or deserts can erase the details geologists need. That is why confidence comes from patterns repeated across separated basins, where different rocks preserve the same story of ice arriving, moving, and withdrawing. In some regions, tillites rest on older surfaces cut by grooves. Elsewhere, dropstones puncture fine lake or seafloor mud like sudden impacts. A dropstone falls from floating ice, sinking through quiet sediment and deforming layers beneath it, a tiny event with a powerful climatic implication. Even without seeing the glacier, scientists can infer floating ice nearby, because ordinary currents rarely place a lone boulder inside undisturbed mud. Taken together, tillites, erratics, striations, and dropstones transform scattered outcrops into a moving geological narrative, pointing toward an ice-dominated world. But rocks record more than motion. Their minerals and isotopes also remember the ocean and atmosphere, carrying us from visible scars to chemical fingerprints. The scars of ice are only the beginning. Within those same rocks, chemistry preserves clues about seawater, air, and the timing of environmental change. Among the most revealing clues are iron formations, layered deposits that form when dissolved iron meets oxygen, sulfur, or minerals settling through ancient water. Today, much oceanic iron is locked away in familiar ores, but its abundance and texture can expose waters that once behaved very differently. During prolonged glaciation, ice could isolate the sea from the atmosphere, allowing oxygen-poor deep water to accumulate dissolved iron supplied by seafloor reactions. Volcanic gases and hydrothermal vents added metals from below, while darkness and restricted circulation reduced the pathways that normally remove them. When iron-rich water finally encountered oxygenated surfaces, iron precipitated rapidly, building bands whose chemistry could preserve a snapshot of changing ocean conditions. Yet these bands are not automatic proof of a completely sealed ocean. Currents, basin geometry, and local volcanic activity could produce similar signals. That caution is why geologists read iron formations alongside sulfur minerals, trace elements, and the sediments enclosing them, comparing several chemical stories at once. Sulfur offers a particularly sensitive record, because its isotopes can distinguish ordinary biological cycling from reactions driven by light, oxygen, and volcanic gases. Some cryogenian rocks carry isotope patterns, unlike those expected from a modern, oxygen-rich ocean, hinting at unusual sulfur reservoirs and limited exchange. The meaning is subtle. A strange isotope signature may reflect global conditions, but it can also record a restricted basin or later alteration. Researchers therefore test multiple grains, compare neighboring layers, and search for mineral relationships that survived burial, heating, and chemical overprinting. Carbon isotopes provide another window, tracking how carbon moved between seawater, volcanic carbon dioxide, buried organic matter, and minerals forming on the seafloor. If photosynthesis, weathering, and burial shifted dramatically beneath ice, the carbon record could register that disruption long after the frozen surface disappeared. Rare earth elements add a different perspective, revealing whether sediments received material from continents, hydrothermal fluids, or chemically stratified seawater. Their proportions can expose the balance between weathering on exposed land and precipitation within the ocean, even when the original ice is gone. Minerals themselves become witnesses. Pyrite points toward low oxygen settings, while manganese oxides require oxygenated conditions and a pathway for oxidation. Together, such assemblages can map chemical boundaries through ancient basins, showing that a single ocean may have contained sharply contrasting environments. This matters for Snowball Earth, because the model predicts isolation but not perfect uniformity. Water beneath ice could still circulate through fractures and openings. Tidal motion, geothermal heating, and submarine volcanism may have created refuges where fluids mixed, nutrients concentrated, and chemical gradients remained available to life. Isotopes cannot photograph that hidden world, yet they can reveal its consequences. Uneven oxidation, localized metal deposition, and changing pathways through the seafloor. The strongest interpretations emerge when microscopic textures, field relationships, and whole rock chemistry agree, turning scattered clues into a coherent environmental sequence. That sequence often begins with restricted, oxygen-poor waters, proceeds through iron and sulfur reorganization, and ends with evidence for renewed contact with the atmosphere. Renewed contact is crucial because it suggests the frozen state eventually broke, releasing stored chemical imbalances into oceans that were suddenly changing. And above the glacial deposits, the rocks record that aftermath in a striking new layer, carbonate laid down as the planet began to thaw. That layer above the ice is not merely another sediment, it is a cap carbonate, a thin geological exclamation mark after planetary freezing. Across several continents, these carbonate beds appear with uncanny timing, resting directly on glacial sediments, as though thawing had opened a new chapter. Their name describes their position. They cap the Ice Age deposits. Their meaning, however, reaches deeper, into the chemistry of a rapidly changing ocean. To understand the clue, imagine a seafloor buried beneath drifting debris, then suddenly exposed to warm, alkaline water loaded with dissolved carbon. That chemical transition could make carbonate minerals crystallize quickly, coating the ocean floor in pale rock, while the last ice continued to retreat. But the rocks are not identical everywhere. Some form smooth, massive sheets. Others contain unusual textures, cavities, and delicate structures unlike ordinary marine limestone. These differences matter because cap carbonates were products of environments in motion, shaped by temperature, alkalinity, ocean circulation, sediment supply, and local seafloor relief. Their most famous feature is their abrupt appearance. A sharp boundary separates them from glacial deposits below, preserving a transition from glacial deposition to open water chemistry. In places, the contact is so clean that it feels instantaneous. Although geology rarely records a single moment, it records overlapping processes compressed together. One process may have begun with intense weathering on newly exposed land, drawing carbon dioxide from the air and carrying dissolved ions toward the sea. Another involved the ocean itself. As circulation restarted beneath thinning ice, stored chemical gradients could collapse, changing seawater into a factory for carbonate precipitation. This helps explain why the cap can be thick, widespread, and compositionally strange, even when its underlying glacial deposit looks remarkably ordinary. The carbonate may also record a greenhouse atmosphere. During the freeze, volcanic gases could accumulate because cold oceans and ice limited their removal. When deglaciation began, that stored carbon dioxide helped drive warmth, while weathering and ocean reactions converted atmospheric excess into minerals preserved on the sea floor. The sequence is powerful because it links climate, atmosphere, ocean, and sediment in one readable order. Glacial material first, carbonate second, transformation visible in stone. Yet a cap carbonate is not a stopwatch. Its minerals can grow over extended intervals, and later fluids may alter the original chemical signal. Geologists therefore compare textures, trace elements, carbon isotopes, and regional relationships, asking which features formed during thawing and which arrived much later. They also test whether the beds truly follow glacial deposits across broad regions, or whether similar carbonates belong to separate local events with different causes. That regional consistency is crucial. A signal repeated across distant ancient margins suggests a planetary disturbance, not simply a peculiar lagoon, basin, or shoreline. The strongest examples preserve this relationship across continents now separated by oceans, implying that the climate event connected landscapes once joined within an older supercontinent. Still, scientists debate the exact intensity of the thaw. Some evidence favors a dramatic transition from near-global ice, while other interpretations allow open water. What remains difficult is measuring rate. Did carbonate accumulate within thousands of years, or over a longer recovery that only appears sudden because sedimentation was uneven? Every answer changes the climate story slightly, but none erases the central observation. The world froze, then seawater chemistry shifted with startling speed. Cap carbonates became the bridge between two planetary states, turning a simple rock boundary into evidence for feedbacks operating from atmosphere to ocean floor. This pale layer therefore becomes our starting point for understanding how the frozen planet escaped its climate trap and opened toward a transformed world. For millions of years, volcanic gases accumulated above the ice because cold oceans could no longer absorb carbon dioxide through ordinary weathering. Every eruption added another invisible blanket, while the frozen continents locked away carbon and silicate reactions slowed almost to a standstill. The atmosphere thickened gradually, yet the surface remained bright and reflective, returning sunlight to space and delaying the moment of release. Then carbon dioxide crossed a threshold, and even a dim warming began melting ice at the edges, where darker ground absorbed more sunlight. That small advantage became a planetary feedback. Less ice meant less reflection, greater absorption, and still faster melting across widening belts of exposed sea. As dark ocean water opened, it drank in sunlight and heat, transforming a cautious thaw into a runaway transition from white to blue. The ice did not simply vanish. It fractured, floated, and collapsed in enormous rafts, exposing seawater that had been sealed away for ages. Meltwater surged toward the oceans, carrying dust, salts, and minerals, while fresh surfaces weathered violently beneath an atmosphere suddenly rich in carbon dioxide. That weathering consumed the excess gas, but only after the greenhouse pulse had driven temperatures far beyond anything familiar from ordinary ice ages. Near the equator, glaciers retreated through landscapes that had endured darkness, revealing sediments ready to record the violence of their disappearance. Rivers first ran beneath melting margins, then spread across newly exposed plains, carving channels through debris and feeding swollen, mineral-rich seas. The oceans changed quickly as fresh water diluted their surfaces, while buried nutrients and dissolved iron entered waters that had been chemically isolated. In some basins, oxygen returned unevenly, creating sharp chemical boundaries where new currents met stagnant deep water and altered ancient mineral balances. The climate overshot its target, replacing frozen stability with searing humidity, violent rainfall, and temperature extremes that lasted far longer than the thaw. This was not a gentle return to normality, it was a planetary whiplash, with heat accumulating faster than ecosystems could immediately reorganize. Some organisms found new opportunities in illuminated waters, while others faced heat, salinity shifts, disappearing habitats, and competition from rapidly expanding survivors. Above them, storms became engines of erosion, stripping fresh rock and delivering chemical ingredients into seas already transformed by the atmospheric upheaval. The record suggests that deglaciation happened rapidly in geological terms, even if its exact speed remains hidden between layers of disturbed sediment. And because the ice ages ended more than once, Earth repeatedly entered this dangerous sequence: buildup, collapse, overheating, and gradual recovery. Each episode tested the same planetary machinery, but continents, oceans, and living communities had changed, making every rebound slightly different from the last. That repetition matters, because it turns a spectacular catastrophe into an experiment, showing how strongly climate responds when feedbacks push it past familiar limits. The rocks preserve the aftermath in cap carbonates, altered minerals, and shifting isotope signals, each recording a different stage of the escape. Together, these clues point toward a carbon dioxide-rich atmosphere, a collapsing ice shell, and a climate suddenly racing beyond equilibrium. Yet the details remain contested. Perhaps open water survived, perhaps ice was thinner, but the transition itself was unmistakably dramatic. By reading that transition carefully, we can see not only how Snowball Earth ended, but why its frozen extremes still challenge our understanding of climate. After the violent thaw, the rocks leave us with a question that demands precision. What does Snowball Earth actually prove, and what does it merely suggest? They prove that cryogenian glaciers reached astonishingly low latitudes, in places where geological evidence records environments that once seemed far too warm for ice. Tillites preserve jumbled debris, dropstones puncture quiet sediments, and striated surfaces show ice moving across rock with unmistakable force over time. These features are not climate metaphors, they are physical traces of glaciers, preserved long after the ice itself disappeared from the ancient world. When those deposits appear in rocks formed near ancient tropical latitudes, the case for extraordinary global cold becomes difficult to dismiss. But geology rarely hands us a complete snapshot because continents move, oceans open, and later burial can erase the context surrounding every clue. That uncertainty matters because the phrase Snowball Earth describes a powerful model, not a single observation extracted from one perfect ancient photograph. The strongest version imagines ice covering nearly the entire ocean, sealing the planet beneath a bright shell that reflected sunlight back into space. Yet the rocks themselves do not always reveal whether open water survived, at the equator, around volcanoes, or within seasonally thawed refuges. Those possibilities belong to interpretation, supported by chemistry, modeling, and biology, but they cannot be settled by glacial sediment alone. Chemical clues broaden the picture. Iron-rich layers suggest oxygen-poor waters, while unusual isotopes record disrupted carbon cycling during prolonged climatic isolation. Cap carbonates add another striking signal, appearing directly above glacial deposits, as though an extreme freeze ended beneath a radically altered sky. Their chemistry fits rapid deglaciation and intense weathering, yet exact temperatures, ice thicknesses, and thawing rates remain matters of ongoing debate. Even the duration of each glaciation is difficult to pin down, because erosion and tectonic recycling have removed pages from the record. So a careful conclusion sounds less cinematic but more convincing. Cryogenian Earth experienced repeated, exceptionally severe glaciations with global consequences. The evidence strongly supports extreme ice expansion. It does not force every detail of a completely sealed, uniformly frozen planet. That distinction is not a weakness. It is how scientific explanations become stronger by separating durable observations from assumptions that can change. And whatever the final boundary of the model, these rocks reveal a climate system capable of crossing thresholds with consequences beyond ordinary human intuition. That is why Snowball Earth still matters today, not because ancient climate repeats modern history, but because feedbacks remain part of the same planetary system. Ice still reflects sunlight, carbon dioxide still traps heat, oceans still redistribute energy, and small changes can still amplify into planetary transformations. The ancient record therefore acts as a stress test, showing how slowly building pressures can eventually produce abrupt and almost unimaginable change. It also offers humility. A planet may look stable for millennia, then reorganize its climate when feedbacks push beyond a hidden threshold. In the end, the rocks do not give us a frozen photograph of Earth, but a record of instability, resilience, and planetary surprise. Their message is both narrower and larger than the legend. Ice truly spread extraordinarily far, and the Earth truly found a way back. That is the enduring lesson, written in stone. Extremes can reshape a world, while recovery begins long before anyone can see it coming.